the seminar. And today, welcome everybody to the Asia Pacific Analysis and PDE seminar. And today our speaker is Po-Lam Yung from the Australian National University. Professor Yung received his PhD in 2010 at Princeton University in the United States under the supervision of Elias Stein. From 2010 to 2013, he held the Hill Assistant Professorship at Rutgers University, where I guess you got to know Haim. And following this, he became a Titchmarsh Fellow from 2013 to 2014 at the University of Oxford and Assistant Professor at the Chinese University of Hong Kong from 2014 to 2020. In 2020, Professor Yang was promoted to Associate Professor at CUHK, while he's on leave actually, because he, in the same time since 2019, he accepted an ARC Future Fellow at the Australian National University in Canberra. So recently he was awarded with the prestigious Antonio Ambrosetti Medal for his new and surprising characterization of the Sobolev norm. And he will speak today about his results and further continuing work about this. So the title is Sobolev Spaces Revisited. Please, Po-Lam, start the lecture.
All right. Thank you very much. Can you hear me well?
Yes, very good.
Right. Yeah. So today we will work on Rn when n is just something bigger than or equal to 1. We will be focusing on the homogeneous Sobolev space W1P and also the homogeneous space BV, the space of functions of bounded variation. So I thought I would start off by just giving the definition of these spaces, reminding everybody what these are. So for P that is finite but bigger than or equal to 1, the homogeneous Sobolev space W1P is the space of all locally integrable functions U modulo constants whose distributional gradient is in LP. And then you can take its norm by computing the LP norm of the gradient of U. So you just integrate the P power of the norm of the gradient on Rn and take this P for it. That is the norm that you would have on this homogeneous Sobolev space. I had to quotient out by constant so that this is an actual norm. Now, on the other hand, the BV space, the space of functions of bounded variations, would consist of all locally integrable functions U, again modulo constants, whose distributional gradient is a finite Redon measure. So just write M here for the set of all finite Redon measures, vector value finite Redon measures on Rn. In other words, sometimes it's written this way. So you take the set of all locally integrable U, and you integrate that against divergence phi of x, where phi is a nice smooth vector field with complex support on Rn, for which the subnorm of the components is bounded about by 1. So take the supremum. This is an this is the quantity that's equivalent to the measure of the gradient of U in the sense of distributions. So this is the BV norm here. In particular, if the gradient of, if U is in W11, then it is in BV as well. So BV contains as a subspace the space of the W11. Right. So in the work that we'll be discussing today, initially joined with Brezis and Schaftingen, we would compute the gradient of U in LP on Rn for U that's, let's say, smooth with complex support. This time, instead of using the gradient where you take the limits of difference quotients, we would try to use only difference quotients and not take the limits as the difference tends to 0. And we will not use any gradient. Okay. And together with Andreas Seeger, we have extended this formula to not just U that is smooth with complex supports, but also U that is in this homogeneous Sobolev space W1P or U in BV. In fact, we found not just one formula, but a natural one-parameter family of such formula. And this one-parameter family of formula can be used to recover certain Galeardo-Liebenberg interpolation inequalities due to Cohen, Delman, Delbouches, and Devaux. And it also allows us to go beyond the range where these inequalities hold. and prove certain substitutes when these inequalities actually don't hold. And our formula for this gradient of U in LP is going to be computed in terms of a weak LP quasi-norm on the product space R2n. So you take a product of Rn with itself. And since it involves this weak LP, maybe it is appropriate to begin by reviewing a little bit the notion of weak LP. Technically, it has a quasi-norm, but I think I would inadvertently just say that the weak LP norm instead of a quasi-norm because it's just easier to say it like that. Okay, so what is that? Well, for P that is finite and bigger than equal to 1, if F is in LP respect to some measure, then we know what the P power of the LP norm is. It is just integral of the norm of F to the power P respect to the measure. Now, this is certainly at least the measure of absolute value of x bigger than lambda multiplied by lambda to the power p for every lambda that is positive. In fact, you just have to integrate over this smaller set, and then over that smaller set, absolute value of f is bounded below by lambda. So this is just Chebyshev inequality. And this is true for every lambda that is positive. In particular, if you take this right-hand side here and take its p root, then when you take supremum over lambda, it is a finite quantity. But of course, the converse is not necessarily true. So what happens is that if f is a measurable function, and the supremum here is finite, then we call f a function that is in weak LP. It is a weaker condition than being in LP. And its weak LP norm is defined to be this supremum here. And we'll write it as the LP comma infinity norm of f with a square bracket that denotes that it is a quasi-norm. And the typical example, which will also be relevant for us later on, is this function f of x, which is norm x to the power minus n over p in Rn. This function is in weak LP because if you look at the size of these level sets, so the set of all x for which this function is bigger than lambda, it is really just a ball. It is the set of all x for which its absolute value is bigger than smaller than lambda to the power minus p over n. And you can compute the big measure of this ball. So I'm using this symbol here, Ln, to denote the big measure on Rn. So this measure here is equal to a multiple of lambda to the power minus p. And that's what you need in order for the function to be in weak LP. But of course, we all know that this is not in LP with respect to the back measure. If you integrate that, you are integrating, if you integrate f to the power p, you are integrating x to the power minus n, which is of course infinite on Rn. Okay, so this is about weak LP. Now on this slide, there are two quantities that I would like to highlight that these conventions will be used throughout this talk. The first one here involves a first order difference. So if h is a vector in Rn, then this operator delta h of u is just u of x plus h minus u of x. So you're just taking the difference when you have an increment h. It might be believable that the gradient of u of x is somewhat similar or comparable to this difference quotient here, at least when h is very small. So if we want to express this gradient of u in LP using a difference quotient instead of a gradient, it might make sense to try, at least initially, to look at the double integral of this difference quotient raised to power p respect to the Lebesgue measure, dx dx. So that at least formally it looks similar to this expression here, the integral of the norm of the gradient to the power p. Now, this is not going to work for a simple reason. If you replace u of x by u of tx, where t is some parameter that's positive, then the two sides of the two quantities that you have up here do not scale in the same way. So dilation invariance tells us that there is no hope of doing so. In order to achieve the proper scaling, what one has to do is to modify the measure here. So you should have a measure that's not the big measure dx, but you have got to divide by norm h to the power n. And then it will scale correctly, just like the integral of the gradient of u to the power p. Now, this kind of difference quotient is going to arise a lot in this talk. So I'm going to give it a name here. Well, what happens in the numerator, you have the absolute value of this first order difference, ux plus h minus u of x. And the denominator is just norm h to some power b. And the only thing that changes is the number b. So I'm going to keep track of the number b by saying that this is the quotient qb of u. B is just the power that you have in the denominator. If we use this convention, then this quantity, this double integral up here, can also be written as a double integral with respect to the big measure. And what you do is that you take the p power of the difference quotient, where the denominator is 1 plus n over p. In fact, if you take 1 plus n over p, like you have a denominator h to the power 1 plus n over p, and raise it to power p, that you do when you take the LP norm. This is precisely the numerator that you see here, norm of h to the p times norm of h to the n. Okay. So again, two pieces of convention that will be useful for us is this difference operator delta h and this quotient qb. In fact, I got to remind you here already that this is the convention that we had on the last page. Well, for s that is strictly between 0 and 1, and for p that is bigger than or equal to 1 but finite, sometimes people define a fractional Sobolev space WSP, so a fractional one because s is less than 1. And they define it as the space of a locally integrable u for which this quantity here is finite. Well, so what is this? This is the double integral of the p power of the difference ux plus h minus u of x to the power p divided by h to the power, initially s plus n over p raised to the power p. But it might be a little bit easier to, I mean, it's a slightly more conventional to write this as p plus n, if we simplify. And this is the double integral that we're looking at. Okay, so this way it is perhaps a little bit more conventional how people write it. Now, when p is strictly between 1 and infinity, this WSP norm is actually known to be equal to, it's known to be comparable to the BSPP norm of your function u. The space here is actually coincide with the diagonal best of space BSPP, and the norms are comparable. And this is the fractional situation where s is strictly less than 1. So it might it might make sense to ask again whether or not you should just replace s here by 1 and compute the LP norm with respect to the big measure of this difference quotient, where the power in the denominator is 1 plus n over p. Would then give you the gradient of u and LP? Well, the answer turns out to be no, unless u is identically 0. If you take this LP norm on the product space R2n, if u is not identically 0, but let's say something else is C infinity with complex support, you can calculate what this norm is. This LP norm is always going to be infinite. So it doesn't give you the gradient of u and LP, it always gives you infinity. And the issue here is simple. In this denominator, there's always h to the power minus n over p somewhere. And then if you integrate this, I mean, if you take this function with respect to LP of dx, this is not LP with respect to dx, so this dx should not be there. Dx should be here. This h to the minus n over p is not LP with respect to dx on Rn. Okay. So we can't quite take the LP norm of this difference quotient with denominator 1 plus n over p. That wouldn't work. And for context, I think it is helpful to mention this also very famous formula by Bogan, Brezis, and Mironescu about 20 years ago. They explored what happens to the WSP norm of U as S tends to 1 from below. So on our end, it says that, let's say U is C2 with complex support. For P that is bigger than or equal to 1 but finite. If you take the P power of this WSP norm and let S tends to 1, you get infinity, usually. But if you multiply by this factor 1 minus S in front of it, which of course tends to 0, as S tends to 1, then the product will have a reasonable limit as S tends to 1. In fact, this is going to be some explicit multiple of the gradient of U in LP raised to the P power. Here, you've some funny constant Kpn here depends explicitly on P and N. I've written down its value down here, but the precise value is probably not going to be very important for us today. And in fact, while we are at this, I should also mention that if you take the WSP norm raised to the power P and let S tend to 0, you also don't get something good. But if you also multiply by S, which tends to 0 as S tends to 0, then results of Messier and Shaponikova would say that this is a multiple of the P power of the LP norm on our end. Okay, so in particular, we see that if I look at this WSP norm, which again is this LP norm on the product space of this difference quotient with denominator S plus N over P, this quantity on its own is not going to have a limit as S tends to 1. It is going to blow up like 1 minus S to the power minus 1 over P as S tends to 1 from this formula up here. Unless U is a constant, in which case it will be 0, but then that's not an interesting case. So this is another indication that if you just blindly plug in S equals 1 in this expression and calculate the LP norm of the difference quotient with a power that is 1 plus N over P, the denominator, this is not going to give you a gradient of U in LP. Then our first main result on the next screen is to offer an alternative point of view that says this time I don't have to vary S. I can fix S equals 1. But instead of taking an LP norm here, what you should be doing is to take a weak LP norm, which is a smaller quantity than the LP norm. So the LP norm will be finite, but if you take the weak LP norm, I mean, the LP norm will be infinite, but if you take a weak LP norm, which is smaller, then you have some chance of getting a finite quantity. And remember, the motivation here is that this H to the power minus N over P, this is not LP, but it is indeed in weak LP. So we do have some chance here from this point of view. All right, so this is the formula. For N that's bigger than or equal to 1, P bigger than or equal to 1, but finite. And let's say initially U is smooth with complex support. Then in this joint paper with Brezis and Schaftingen, we showed that the LP norm of the gradient of U is comparable to the weak LP norm with respect to the Lebesgue measure of this difference quotient here, where the denominator has a power 1 plus N over P. So if I write the difference quotient out a little bit more explicitly, this is the weak LP norm of this difference quotient on the right-hand side. Remember, delta H of U is just U of X plus H minus U of X. In particular, if I unravel this a little bit, then for lambda positive, I can look at the superlevel set of this difference quotient that I have in this weak LP norm. Look at the sets of all X and H, where this difference quotient here has absolute value bigger than lambda. Then if you look at the Lebesgue measure of the set multiplied by lambda to the P, you take subprimum over all lambda that is positive. This is comparable to the gradient of U in LP raised to the power P. In fact, we also have a second formula here. So this is the first formula that allows you to compute the gradient of U in LP up to a multiple. But we have actually a second result here that is also quite nice, and that it tells you what the gradient of U in LP is up to like a constant multiple, not an explicit constant multiple. You can compute the left-hand side by computing the right-hand side here. It is an exact equality. What it says is that if you, instead of taking the supremum over lambda of this quantity lambda to the p times the big measure of E lambda, let's say you take the limits as lambda tends to infinity instead. The first claim is that the limit is going to exist. The second claim is that this is exactly equal to an explicit multiple of gradient of u in LP raised to the power p. Right, so I have some comments in the next slide, but I think it's also probably a good time to pause for questions if there's any. Okay, so maybe I'll just go on. So first of all, this power 1 plus n over p in the denominator. It is somewhat important, but not so important after all, because it's going to be dictated by dilation invariance. In fact, if you have QB, the difference quotient with denominator B, if it is weak LP norm with respect to the big measure is going to scale like the gradient of U in LP, then by a scaling invariance argument, you can show that B would have to be this 1 plus n over P. So there's only one value of B for which this works. And in fact, this happens for every theorem that I'm going to state today. So in a way, you can forget about the precise power in the denominator as long as you know what theorem we're dealing with. Like that particular power, there's only one power for which it works, and if it works, then it's that particular power. So it's not wicked to say that there is some B for which this theorem holds. That is actually an equivalent statement. And also, how do we actually prove this? Well, the first claim in the theorem was that if we look at the weak LP norm of this difference quotient, it is comparable to the gradient of U in LP. But in fact, we only need to prove an upper bound. We only need to prove this side of the inequality here after we know the limit equality here. Because the left-hand side of this inequality, namely the weak LP norm, it is a supremum over lambda. And for any function of lambda, the supremum over lambda is always at least as big as the limits as lambda tends to infinity, if the limit exists. So if I know that the limit of as lambda tends to infinity of this quantity is already a multiple of gradient of U in LP raised to the power P, then all that remains is to prove a reversed inequality. I would have to prove that the supremum here is bounded above by the gradient of U in LP. That's the only thing that we need to do. And that can be done using a covering argument. It is an argument using a Vitelli covering lemma. In fact, what motivated us was the proof of the harder literal maximal function that is bounded from L1 to weak L1. This is a standard proof that we all teach in a graduate course in analysis. And it is that kind of covering lemma that we will need to use in this proof. So recently, there's also been work of Dai, Lin, Yang, Yuan, and Zhang, who extended our proof to certain metric measure spaces of homogeneous type, spaces of homogeneous type. So I won't say much more about this, but maybe I should just also add that the limit equality can actually be proved using Taylor expansion in a way that is somewhat reminiscent of the proof of the Brezis-Marinescu formula, the PBM formula that we have seen earlier. Okay, so this is an overview of this initial theorem. But then it turns out that we wanted to understand what happens for general U in W1P or general U in BV. And what we found is not just the formula for U in W1P but BV. It is also a one parameter family of such formula. And this is a natural one parameter family. In fact, in some of the applications I'll be giving you later on, it is necessary to have a one parameter family to obtain the full results. If you have only got one result, then we can't prove the theorems that we'll be discussing at the end. So what happens? Well, this one parameter family is going to be indexed by a real parameter gamma. And we are going to consider a measure on the product space R2n. Instead of dx dh, I have a power of h raised to power gamma minus n. This is the way that we labeled it. And then d nu gamma is this measure here. So earlier we were dealing with the big measure, which doesn't have this factor. So that was the case gamma equal to n that we had earlier. But this is like for general gamma, this is different from what we had seen earlier. So what happens? Well, this is quite tricky. So let me just first of all state it for the range where p is strictly bigger than 1 but finite. There will be some other things about p equals 1 on the next 2 slides. But for p that is strictly bigger than 1, and let's say u is in the homogeneous Sobolev space W1p. For every non-zero gamma, you can compute the weak LP norm with respect to nu gamma, the measure here. You got to choose a suitable power in the denominator in order to do that. But assuming that you choose the correct power, which happened to be 1 plus gamma over p, then you will get the gradient of u in LP. Now up to some comparable constants. That of course changes from different from when you vary u. But okay, so this is the first result. And furthermore, if we look at the super level set of this suitable difference quotient, where the set of all x and h, where this is bigger than lambda, and let's call it E lambda, then you can look at lambda to the p times nu gamma of this E lambda. This E lambda is of course going to depend on gamma because the difference quotient here depends on gamma. But if you look at the nu gamma of this E lambda and multiply by lambda to the p, now it depends on whether lambda is positive or negative. If lambda is positive, you will let lambda, the height, go to infinity. If lambda is, if gamma is less than 0, then you will let the height lambda tend to 0. In either case, you get an explicit multiple of the gradient of u in LP raised to the power p, the W1p norm of u. Right, so this is somewhat reminiscent of what we had seen earlier, except this is now for all gamma that is non-equal to 0, and for p that is strictly bigger than 1. The case where gamma equals minus p of this limit equality here, so this other result when gamma is -1, this has been proved by Yuan about 10 years ago. All right. For p equals 1, we have a similar theorem for BV, but with a number of additional twists. So first of all, let u be in BV. Then initially, let's consider the range of gamma here. The range of gamma is that gamma is not between -1 and 0. So not just non-zero. Earlier, your gamma is just non-zero, but this time you got to remove a whole interval here. Then if you compute the weak L1 norm with respect to nu gamma of a suitable difference quotient, the denominator has a power that matches this gamma, then you would get the BV norm of u, which is again the measure of the gradient of u. Furthermore, you look at the size of the super level set called E lambda. Compute the nu gamma of this super level set, multiply by lambda. If lambda is positive, you let if gamma is positive, you let lambda to positive infinity. If lambda is less than -1, then you let lambda to go to 0. In either case, you recover a multiple of the BV norm. But this time, it is only true for functions that are in W11. So this formula here holds true for all u that is in W11, but it can actually fail for BV functions u. In fact, what happens is like if you take u to be the characteristic function of a bounded domain with smooth boundary that I call omega in Rn, any such domain, and you compute the quantity on the right-hand side, the limits here, these limits will exist. But instead of being equal to the same multiple of gradient of u in measure, you would get a different multiple of the measure of gradient of u. And I find that quite interesting because you can actually detect the regularity of U by taking these limits. If U were in W11, you get one answer. If U is in BV but not in W11, then you could have gotten another answer. Okay, so this is for the range where gamma is not in this interval -1 to 0. And something bad happens in this interval. For gamma that is in this interval from -1 to 0, if you look at the weak L1 norm of this difference quotient respect to new gamma, and you look at the sets of even smooth functions with complex support for which the W11 norm is equal to 1, the supremum here is infinite. So there's no way you can compute the gradient of U in L1 by looking at this quantity here, if gamma is in this forbidden range. Furthermore, you might wonder what happens if I look at the limits as lambda tends to 0 of lambda times the size of the superlevel set with respect to new gamma. So gamma is now negative, so it makes sense to look at what happens when lambda tends to 0. You might ask whether or not it is equal to this multiple of U and BV. This time, this formula here holds for all U that's C1 with complex support. But the formula, as stated, would fail for U that is in W11. And in fact, the failure is so bad that it is a generic failure in the sense of Bayer category. So it's quite delicate here. Some formulas hold true for some class of functions, nice enough functions, but then as long as the regularity is a little bit worse, then the formula fails. And I should mention that the case gamma equals -1 of this limiting formula that it holds for all U in C1 with complex support but fails for W11. This is something already established by Brezis and Yuan a little bit earlier. And the failure of this limiting formula in the case where gamma is strictly between -1 and 0 turns out to rely on some construction of a Cantor set of fractional dimension 1 plus gamma. So of course it doesn't work when gamma is -1. There's no Cantor set of dimension. I mean, we're not going to construct a Cantor set of dimension 0, but yeah. But then for gamma it's strictly between -1 and 0, some self-similarity actually kicks in. Okay, so this is what happens for p equals 1. Earlier we had a theorem for p bigger than 1, but all these theorems assume at the outset that U is either in W1P or U is in BV to begin with. So we asked whether the formulas we had hold for U in W1P or U in BV. But we can actually also turn this around and characterize using these formulas functions in W1P for p bigger than 1 and functions in BV when p equals 1. This uses the BBM formula, and this is the result that I have on the next slide. Now, let U be locally integrable to begin with. That's the a priori assumption. And suppose gamma is just any real parameter. If the weak LP norm with respect to this new gamma of a suitable difference quotient is finite, then you can actually conclude that U is in W1P if P is bigger than 1. You can conclude that U is in BV if P is equal to 1. So in particular, for locally integrable functions U, if P is strictly between 1 and infinity and gamma is non-zero, then U is in W1P if and only if this weak LP norm of this difference quotient with respect to new gamma is finite. And there's a similar statement for BV, but of course this time I got to remove a larger interval for gamma in order for it to be an if and only if. Right, so this is a long list of results. I think it is best to illustrate that with some applications. And in fact, the existence of such one parameter family may look complicated at the beginning, but it is actually natural and argue that it is actually useful in applications, as we will see. Right. So it is about Dirichlet-Lyrenberg interpolation. And this is initially due to Cohen, Diamond, Double-Sheets, and DeVore. So let's look at the plane that parameterizes 1 over P and S. And I'm going to look at the WSP norm of a function by picking up points in this space. So if, let's say, T is strictly between 0 and 1, and Q is strictly between 1 and infinity, and let's say T is strictly less than 1 over Q, I will put down a point on the plane here that corresponds to WTQ by labeling the points that has coordinates 1 over Q, comma T, right? And the statement that the assumption that T is strictly less than 1 over Q is just going to say that this point that I have drawn in green here is below this dotted line that makes a 45-degree angle with the axis. So pick any point T, comma Q in this region. And then what happens is that if U is both in BV and in this WTQ, then draw the blue line in between these two dots. By the way, the point BV should correspond to the point 1, 1, right? Somewhat similar to W11. So draw the blue line between these two dots. Then for any pair SP that is on this line, you will be able to say that U is in WSP with this inequality here. So U in WSP is bounded by the correct powers of U in WTQ and U in BV, the power being dictated by where this point is. The parameter theta decides where the point is on this line by this equation here. Okay. So one thing to note here is that if I have this assumption that the point WTQ lies below this dotted line, then the line that I've drawn, the blue line that I've drawn, would necessarily have slope that is strictly bigger than 1. And this is going to play a role in what follows. So the original proof of Cohen, Diamond, Double-Sheets, and DeVore uses bounds for coefficients of certain wavelet expansions of a general function in BV. And we can give an alternative proof that's quite nice and simple based on our theorem for BV, which I'll show you in the next screen. So again, I'll remind you that the slope here is really important. It is something bigger than 1. In fact, I'm going to let gamma be -1 times the slope. So I have the concrete expression here, but it is really just -1 times the slope of the straight line. And the main points being gamma has to be less than -1 now because the slope is strictly bigger than 1. Then remember, since gamma is strictly less than -1, for functions that is in BV, I could have written the BV norm in terms of the weak L1 norm with respect to this new gamma, this measure, with a suitable power in the denominator of a difference quotient. On the other hand, the WTQ norm is given by the LQ norm with respect to new gamma of some difference quotient here. And this is just because the WTQ norm was by definition this double integral raised to power 1 over Q, where you have TQ plus N in the denominator. And if I write down the right-hand side here, what you have is a power TQ plus gamma, but with respect to the measure new gamma. And new gamma, I remind you, is precisely h to the power gamma minus n dx. So if you just plug this in, and then the power of gamma cancels out, right? And then you just get exactly the left-hand side here. And this is why this is equal. And the same happens for WSP, happens for any fractional S and T. Now, the upshot here is that we have chosen a gamma so that we have 3 different powers in these denominators of the difference quotients, but these 3 powers, they all coincide. If we choose gamma to be negative of that slope, then these 3 powers happen. I mean, it's a simple algebraic calculation that I will skip for now. But these 3 powers here all coincide, meaning that I'm not talking about 3 separate difference quotients, but this is actually the same difference quotient that I can call capital F here. And there's a general fact about LP spaces in weak L1. So assuming the condition that we have between PQ1 and theta, one can actually have the LP norm of any function capital F being bounded by LQ norm to the power 1 minus theta times the weak L1 norm of F to the power theta. This is a general fact about LP spaces and weak L1 spaces. So if we accept that, we just start to plug in capital F. For the first factor, we plug in capital F equal to this difference quotient of U. Second factor, I can plug in that, and the final factor, I plug in F equals the quotient with denominator 1 plus gamma. And then I just remember all the green formula that I have up here. And then this is precisely what I had to prove. This is the bound for WSP norm of U in terms of the WTQ norm of U and the BV norm of U. So it avoids anything wavelet. It's just a simple manipulation using difference quotients. And what is better is that earlier we saw that we do need this condition T less than 1 over Q in the results of Cohen, Diamond, Double-Schiss, and Devaux. If TQ is in this plane, and then I have this relation between P and S and Q and T and 1, 1. So remember this figure here. We had to assume that T is less than 1 over Q. In other words, assume that the point WTQ is somewhat below this dotted line here in order to have a positive result like that. And it was crucial in our proof because it guarantees that gamma is not in this forbidden range from -1 to 0. In fact, if we look at this inequality here that we wanted to prove, this inequality is false if T is bigger than or equal to 1 over Q, the result due to Brezis and Mironescu. So in other words, if you happen to have chosen a point WTQ that is on or above this dotted line, then try to connect them. You wouldn't be able to connect. Wouldn't be able to bound the WSP norm of U for an intermediate point by the WTQ norm and the BV norm. And the issue here is that the slope is now less than or equal to 1, which means the gamma falls in this forbidden range between -1 and 0. Okay. Nonetheless, we're able to prove a substitute result. So if U is in WTQ and BV, then I can control the Lorentz norm of a suitable difference quotient with respect to nu gamma prime, as long as gamma prime is anything not in the forbidden range. Here, the Lorentz norm is a little bit complicated to define, so I won't go into that. But the parameter R here is given in terms of Q and theta. And we also show that this exponent here is sharp. So it's just work with Brezis and Schaftingen, at least in the case when gamma prime is equal to n, the dimension. Okay, so that's one result. Maybe I would close by mentioning 2 more things. The first thing is that instead of the gradient of U in LP, it turns out to be also possible to obtain a formula for U in LP using a similar framework. So remember, we have this measure nu gamma defined on R2n, the product space. So suppose U is in LP, P bigger than or equal to 1 and finite. For gamma that's non-zero, if we look at the weak LP norm with respect to nu gamma of a suitable difference quotient, this is also going to be comparable to the LP norm of U. Furthermore, if I look at the size of the superlevel set, then look at the lambda to the power p times the measure of this superlevel set with respect to nu gamma. If gamma is positive, this time is a little bit reversed. I should take lambda, the height, to go to 0 if gamma is positive. If gamma were negative, I should take lambda to positive infinity. And then I would recover a multiple of the LP norm of U to the power p. Again, this constant here is explicit, depends only on n and gamma. In fact, it's twice the surface area of the sphere divided by norm of gamma. And this appeared in joint work with Chin Song Gu. Now note that this is not a characterization of LP because the weak LP norms are finite. In fact, 0 if U happen to be a non-zero constant. So if you have a non-zero constant, of course, it's not going to be an LP of Rn for any P, but then the difference quotients would be identically 0. So you can't say that if this weak LP norm is finite, then U is an LP. That's just false. And I would close by saying that recently there's been some extension by Oster-Dominguez and Mario Millman of some of the above results for W1P. They put it in an abstract framework. They showed, for instance, that if X is a sigma finite measure space, P is bigger than or equal to 1 but finite, and TT is a family of sublinear operators on LP of X. So that, well, then for any F in LP, that this estimate here is true. So capital TT of F is strictly approximately to F in L infinity at a given rate. If this is true for F in LP, for some F in LP, then for this particular F, you can actually recover the LP norm of F in terms of the limits of as lambda tends to infinity of lambda times the size of a superlevel set to the power 1 over P. So this measure here is the measure on X product with the measure, the Lebesgue measure on the T axis. Yeah, and they use it to have many other applications. For instance, they computed what the LP norm of Laplacian U is, what the LP norm of the mixed derivative of U is. They had relations between the LP norm of F with the size of level sets for spherical averages of F, averages over larger and larger spheres. For P that is bigger than n over n minus 1, the creative exponents. They have applications to ergodic theory, etc. So yeah, so that's quite nice. And I think my time is basically up. So I think I will just stop here. Thank you very much.
Thank you, Po-Lam, for this very, very nice talk. Are there any questions by the attendees or remarks? Please raise your hand and I will give you then permission to speak. I have one question, Po-Lam, and that is, would you maybe explain a little bit more in detail at the very beginning of your talk? You mentioned the result with the limit. Mm-hmm. Further, a little bit further, yeah.
Yes. Let's see. Maybe this one or the previous one.
Oh, this one. Yeah.
This one. Yeah.
Can you say something? No, this was already obtained by Brezis and Renescu. I mean, the formula before, the slide before.
Maybe this one?
Yes. Can you give, exactly, can you give a little bit more, a rough idea, maybe a sketch of the proof of exactly this?
Oh, yes. So in fact, one way in which you can understand these different quotients is, so maybe I should just write this out, right? This is like U of X plus H. So maybe minus U. Well, it's actually right up here, so I don't have to write. But we look at this difference quotient, and we are looking at the sets of all X and H for which this is bigger than lambda. Mm-hmm. So let's pretend that for a second that this difference quotient is just norm of gradient U of X divided by H to the power n over P. Mm-hmm. Now, if you look at the set of all X and H for which this is bigger than lambda, and I compute the Lebesgue measure of this set. Okay.
Yep.
And what I do is that first of all, I will integrate over H. And H to the power n over P is less than gradient U of X divided by lambda. So if I look at the norm of H, then if I divided by P over N. This is the condition that I have for H.
Yeah.
And over X, I have to integrate over Rn.
Hmm.
But what is this when I integrate respect to dx and dx? Well, then what I get is basically just the integral over Rn of the big measure of this ball. So this is basically gradient u of x divided by lambda to the power p over n, but raised to power n because it is an n-dimensional ball.
Mm-hmm.
And then I'll be integrating dx up to some constants, right? So if I just cancel out the n here, I would have gradient of u to the power p, which is basically what this term is here.
Mm-hmm.
And then I will have division by lambda to the power p, which I will kill by multiplying by lambda to the p.
Mm-hmm.
So if I believe in this translation between the difference quotient and this quotient involving the gradient, then this formula looks quite believable.
Mm-hmm.
And the claim here is that as lambda tends to infinity, as the height tends to infinity, this approximation is doing that better and better.
Mm-hmm.
Because if the height is really big, then in order for, after U is a smooth function of compact support, right? In order for this difference quotient to be bigger than lambda, it is necessary that H be really close to 0 in order for, I mean, the numerator is bounded, right? The numerator is a bounded function of U and X, of X and H. So in order for this difference quotient to be bigger than lambda, you really need the denominator to be really small. And
Mm-hmm.
for H to be really small, then you might start believing that this difference quotient here is approximately the gradient of U at X divided by norm H to the power n over P.
Mm-hmm.
So that is the connection. Like that is why it is good to take lambda going to infinity if you were to try to prove this formula.
Mm-hmm. Thank you. That's a very nice explanation. Thanks.
Thanks.
Are there other questions? Please raise your hand.
Or explanations.
Yeah, there are.
Some of these things. So.
Adam, please unmute yourself. And
okay, yeah. So just, I don't know, can I make myself visible?
no, unfortunately not. Sorry.
Okay.
Oh.
So anyhow, so you mentioned about some generalization to metric measure space. So basically, I mean, in your talk, you kind of like a gradient is just, I understand gradient on just on Rn. So what are the kind of like basic assumptions? Can we do the things like this on manifolds, compact manifolds, say for on Lie groups or kind of on
yeah,
maybe
so it is the work of these other authors, which I have not entirely understood yet. But from what they say, I think they have something for manifolds, for the gradient on the manifold, for instance, that should be covered in their work. Yeah, and I think they considered some sort of Lipschitz norms on the, like instead of the gradient. Of course, on the metric measure space, you may not be able to talk about the gradient, but then they had some LP estimates for Lipschitz norms of functions, and yeah, so there's some connections to Pointare inequalities in what they are doing, but this is really recent. This is like maybe 3 weeks old, so I'm still in the process.
Okay.
Digesting.
And how about things like say Heisenberg group or Grushin type operators?
Yes, so for the Heisenberg group, I know various people have thought about that. We've also thought a little bit about that. Like I don't think anyone has written anything about it yet, but the belief is that something like that should be true.
Okay, thank you.
Yeah, thank you.
Thanks, Adam, for your questions.
For the Grushin operator, it'll be interesting. I don't know. Yeah. In fact, I have a list of open questions at the end, but I just didn't get to it. So just in case you guys are interested, we have these things. Yeah. So we have a bunch of.
Someone else raised their hand. I think Ben, did you raise your hand? Yeah, please.
Yes, thanks, Po-Lam, for a lovely talk. You had this nice equivalence or characterization of the W1P and BV spaces.
Right.
Do you also get from that a new sort of equivalent expression for the norms, or is that not the case?
Yes. Yes.
You do, yeah.
we do also get equivalents for the norms.
Yeah. Okay.
Right.
Thanks.
Yeah.
Thanks, Ben, for the question.
So the quantity on the right hand side is the equivalent norm.
Mm. Right. Yeah. Are there more questions? If not, then let me thank in the name of all the attendees the speaker for this beautiful talk. And you all should have received an email for to the coffee break, which is just now, will just start in a few minutes, or you can join already actually. And please join us with a favorite drink. And I will close now this session. Po, did you receive the email to the coffee break?
I got to check, but yeah, if you sent it, I should be able to get it.
Yes, okay. Then I hope to see you in the coffee break. And thanks again. And see you next week, everybody. Bye.
Thank you. Bye.